Hi, this is the second video for Math 1105 talking about inverse functions. So in the last video, first of all, let's go back to the last video. We talked about what an inverse relation is and how we know one function has an inverse that is also a function. And we knew that by doing something called the horizontal line test to find out if the function is what we call a one-to-one function. So only functions that are one-to-one have inverses that are also functions. So what we're going to do now is look at taking a function and finding its inverse function. Okay, so there are a set of steps. There's a list of steps on the note sheet. I'm just going to take you through them through the example. They're not very useful just for me to sit here and write down, but I'll write down as we check them off. First thing we need to make sure of is that the thing we're trying to find here actually exists. So we're supposed to be finding the inverse function. Do we know that this thing has an inverse function? Well, since we are in this class, in this very strange semester, the answer is always yes. So every function in this class this semester will be one-to-one and will have an inverse function. So the way you could find this one, though, is you can graph the function. We know what this one looks like. This is a linear function that has a slope of 4 and a y-intercept of 3. So it sort of looks like that without the curves. All right, so this thing definitely passes the horizontal line test. So we know that if we were to find its inverse relation, we could write it in function notation. It would also pass the horizontal line test. So step 1, make sure it's one-to-one, and this one is. Okay, step 2. We're going to simplify our notation a little bit here. So we have f of x equals 4x plus 3, but we could just as well write y equals 4x plus 3. That's perfectly fine. F of x is just a very specific version of the variable y. It's just one that tells you you're looking at a function. So we're going to replace f of x with y. Okay, now step 3, we're actually going to do the inverse step. And we talked about this last time. We do the inverse step just by swapping the coordinates, x and y. We already did that. All right, so there is the inverse relation, but that's not what we're asked to find. We're asked to find the inverse function. So the next couple of steps are dedicated to writing this in function notation, solving it for y, and then calling it a function. So we need to solve this thing for y. So I'll rewrite it. Start fresh. So to get y on a side by itself, our first job is going to be to subtract 3 on both sides. Good start. Then for y to be by itself, we have to divide both sides by 4. And we end up with x minus 3 divided by 4 is y. Okay, this is the most work you're going to have to do in these problems, is the solving for y part. And we found the inverse function. Our last step is just to write that as the inverse function of f of x. So we're going to bring back the function notation and just put the inverse notation up there, the little -1. So f inverse of x, not just plain old y, but f inverse of x specifically, is x minus 3 over 4. Now we talked about it at the beginning of the last video, and by the way, this is our final answer. We talked about it at the beginning of the last video. An inverse relation reverses the operations of the relation. We're going to talk about that a little bit more later, but you can see it happening here. If we look at f of x, imagine substituting in a value for x. What would happen to it? Well, according to the order of operations, we would multiply by 4, then add 3. If you look at the inverse, if we were to substitute in something for x, we would be subtracting 3, then dividing by 4. So we're doing the opposite operations in the opposite order. We're actually reversing the actions of that function, and that's what an inverse function is supposed to do. By the way, it's an inverse function. It will pass the vertical line test. Okay, now I'm going to kind of go off script here. The next couple are really good to do if we're sitting in class and doing them. They're not so great to do on a teeny tiny whiteboard. So we're going to stick with simpler functions this semester to find our inverse functions. So the next two in your notes, just kind of scratch out and make these the ones you're looking at. Okay, so let's look at a function like that. First, we have to make sure it's one-to-one. If we were to write it like we talked about before, whenever we were looking at linear equations, we can split this up over the denominator just to make it look like two parts, mx plus b. So that'll be 1 over 3 times x plus 2 over 3. So that's a line. And we know how to draw something like that. It's got a y-intercept of 2/3 and a slope of 1/3. So this is not a great drawing, but it looks something like that. And so we know this thing is one-to-one. Now, again, for our class, it always will be, but now we know we've proved it to ourselves. So now let's find the inverse function. And you can use this form of the function or this form of the function. I like this one better. So either way, go with it. But our next step was to write y instead of f of x, just because it makes the notation a little easier. Then next, we're actually going to take the inverse step. Let me erase this graph here. And we're going to swap x and y. Now, I was taught a long time ago to put an arrow between these two steps because one doesn't really follow from the other. So I've gotten into the habit of connecting these with an arrow. You don't have to. So now we have made sure this thing is one-to-one. We called it y instead of f of x. X and y switch places. So we found the inverse relation here, but our job is to find f inverse of x, the inverse function. So we now have to write this in function notation. We need to solve it for y. Now, what I would do first here, I don't like denominators in my equation. So I'm going to first multiply both sides by 3. Which I'm perfectly allowed to do. It complicates this side just a little, but it certainly does make this side a lot easier. And now solving for y is pretty simple. We're going to subtract 2 on both sides. And there we go. There's the inverse function, 3x minus 2. Our very last step is to make sure people know what we just found is actually the inverse of this function. So we're going to bring back that function notation. And that's our inverse function, 3x minus 2. So once again, if you look at what happens to x in this function, we add 2, then divide by 3. In this function, we're going to multiply by 3, then subtract 2. So it's the opposite operations happening in the opposite order. It's exactly the reverse of each other. Let's look at one more like this. And then that'll be it. I'm trying to find one that'll work out the way I want it to, but we're probably just going to do one. Let's do f of x equals 1/2 x. Okay, if we were to draw the picture, we know it's going to be 1-to-1 because I already told you. But let's say you didn't. This has a y-intercept of 0 and a slope of 1/2. So it looks kind of like that. So it's 1-to-1. Now we simplify our notation a little bit. Next, x and y switch places. And now our job is to solve for y. So I'd multiply both sides by 2. And so these are gone. They make a 1. And we just have y equals 2x. And very last, we just bring back that function notation so that we don't just have some general y that could be anything. We have f inverse of x equals 2x. And that's our inverse function. So once again, X gets divided by 2 here, X gets multiplied by 2 here. They do exactly the opposite operation. So the way you can tell if a function and another function are inverses, or maybe the way you can prove it, is to do composition of functions. I'm just going to do one example of this. It's not in your homework. It won't be on the test. I just like to show you how this goes back to what we've learned already. So let's look at a couple that we've already seen. I think that's the one we looked at. Okay. So I feel like we already did these. That was our very first example. What happens whenever you apply f to its inverse? What should happen here is that what we'll end up doing, if you write this without the little circle, is f inverse is going to do something to x. And what should happen is that f is going to come behind and reverse all of that stuff. So what net, kind of, if you think about them both working at the same time, what should happen to x is nothing. If we do f inverse and then f, everything f inverse does is going to be completely undone by f. So we should be left with just an x. And that's how you can tell you did it right. So let's see. Remember, with composition of functions, we work from the inside out. So f inverse is going to go first. We know what f inverse of x is. It's right here, x minus 3 over 4. We can try to simplify it, but it's not really, it wouldn't do any good to separate that into two fractions. So there's really nothing to do there. Now we go into f. So we want to go into our function f, and instead of x, we want to substitute in that. So that's what it looks like. Not very pretty. But now you can actually see the inverse happening. This thing that was divided by 4 now gets multiplied by 4. It's gone. This part that subtracts 3, we have something that adds 3. It's gone. So everything that f inverse did to x, right here, f came behind and completely reversed everything. So what really ended up happening to x was nothing. It's just x. And we can also do it in the opposite direction. So remember that composition of functions is not commutative. So if we change the order, usually we get something different. In general, they're not the same thing. But with inverses, they are. So let's look at what happens here. We write it without the circle. Inside out, so f inverse just hangs out for a second. F of x is 4x plus 3. There's no simplifying to be done. Those are not like terms. So the best thing we can do is substitute in for the variable in f inverse. So let's do it. So this goes in place of x. Everything else in the function stays the same. So there it is. So now let's see what happens. So we first do these operations in the numerator. So we have this piece that adds 3, right behind it a piece that subtracts 3. So that action was reversed. We have this piece that multiplies by 4, right behind it a piece that divides by 4. So that action was reversed also. And what are we left with? X. Because these two things are exact reverses of one another, they don't really do anything if you apply one to the other.